Okay, yeah, your lecture topics. So the date of the lecture is going to be determined by hopefully you, but if you don't have a date that you want, or if it's like the dates will be selected like on a first come, first served basis. I'm just thinking of things I need to add to this. If it'll be first come, first served basis on the dates that are selected. So pick your topic earlier so you have a chance to pick your date. If you have a hard time picking a date, I will just pick a date for you. Typically, those that go earlier are marked a little nicer than those that go later, just as a consequence of me seeing what people have done. You'll email me the topic you want to do. It'll be first come, first served basis. Topic you want to do and the date you want to do it. What I don't have here is the instructions to email me, and I didn't say when the lectures will begin. So I need to add that to this. Your base task, yeah, so you got to make a 15 to 20 minute lecture. Topic of your choice, but I give you a selection, but you don't have to pick from the list that I show you. You can do whatever you want as long as I'm okay with it. All lectures are going to be in this format, like everything that you've seen so far in this course. It's basically based on RST. Let me open up PyCharm. Restructured text, which is like the markup language used for Python documentation, RST, restructured text. If it seems intimidating, you're wrong, because it's hilariously simple. Hilariously simple. I'll show you what I mean. And then you use software called Sphinx that will automatically generate the website for you. If you read the README on the course repo, it'll kind of work you through how to like run Sphinx. If you clone the repo and build the virtual environment, you'll have Sphinx, so it'll be fine. But to show you an example, this is what restructured text looks like, okay? Here, I will even show you like the RST for the page that I'm showing you, just so you can see what it looks like. The most complex thing you're probably going to do is a figure, which looks like this. Right? When making it, just basically look at any of the notes, any of the course notes I've already made, and just use that as a template. So yeah, points. This is how you make like titles and section titles and whatnot, subsections with lesser lines. I mean, you can go read all the Sphinx documentation, the Sphinx and restructured text documentation if you want, but honestly, just look at one I've used. Just look at one of the web pages I've made in RST and use that as what you go off. It'll be easier that way. Topics, site. Why is it not there? It's still polling apparently. Computer's being painfully slow right now. Here we go, student lectures. Description. So this is it. In fact, I can fix that typo here. Nah, I'll do that later. This is what it looks like, right? This is the restructured text. This is what it looks like when it gets generated by Sphinx. So don't worry, you don't need to make a fancy web page. The software does that for you. All you have to do is just do the markup RST. And then there you go. Each lecture is going to be submitted. The way it's going to be submitted is through a pull request to the GitHub repo. So you have to make a pull request. And then you have, you just pull. Just pull. I think he's trying to twist it. You just pull. Hey, you don't want to lose that. Yeah, you submit it through a pull request. All right, so I already kind of showed you a lecture on how to make a pull request, but you're going to do it for a whole topic. I have to approve it. That's effectively going to be your submission once you've submitted it in the pull request. And then I might give you feedback on like, explain this more, do that a little bit. There's a gap. You could probably get rid of that, whatever. I give you some feedback. Once it's approved, I accept it. It automatically gets added to the course website, and Sphinx will build it for you automatically. All you end up submitting is like your RST file through the GitHub pull request, and any corresponding like figures or any additional resources that need to go with your lecture. So that generation will happen automatically to get posted to the course webpage. For testing your build, you're going to want to build it locally on your computer. So that's why I read the GitHub repos README to show you how to kind of do that. Potential lecture topics. Here's a list of potential topics. You can pick these if you want. You can come up with your own. Just run it by me first. First come, first serve. I don't want 3 lectures on differential evolution, only 1. So first come, first serve. Lecture dates. In some cases, it's going to be more natural for some topics to come before others, but in general, it's going to be based on a first come, first serve basis on who wants what dates. I'm going to post which dates are going to be. I need to add to this page, 1, how to submit what you want for your lecture and when you want to do it. It'll just be via email. And 2, I need to add the dates. That'll be there, right? But it'll be a first come, first served basis. There'll be like 2 lectures a day. There's 11 of us. So that's 5.5 lectures, right? They're going to start near the end of the month. Submitting a pull request. Yeah, you just submit the pull request. You're going to add it to the student lectures directory. So if you look here, this is the student lectures. First thing you're going to do is make a subdirectory. New. Man. All right, give it a good name. In here, honestly, start with an existing RST file. Call it, yeah, this is a bad name. And then just start with an existing one and just modify it as you need it. That's it. That's how you're going to want to submit it. Man, this computer's being painful right now, isn't it? Provided files, literally just look at any of the files on the GitHub repo as a template. Format, it's got to be RST. How you lay out your lecture, entirely up to you. Marking, points are going to be awarded a little bit more traditionally, like not like the assignments where if you do it, you automatically get points. This one, it's going to be like, okay, was it good, right? Better lectures get better points. It's going to be based on quality and clarity, both in terms of the content itself and how it was presented. The best piece of advice I could give you is don't make it boring. Don't have a boring lecture. Those are always bad. Those are boring. No one listens. No one likes them. Don't have a boring lecture. Cool.
Now, do you put some image in?
Look at some of the examples. Just look for any of the examples with figures. If I go here's an example. Here's how you add a figure. And that figure, comparing distributions, this is under topics, site, topics, parameters. Comparing distributions is, oh no, this is N Queens GA, wrong topic, GA. There. It's in the same subdirectory. So you put like the images in the same subdirectory, and then you use this like tag to say, okay, I want to do this. This is how big I want it, center, and then you can give it a caption. That's how you do it. Just look for everything. You should be able to find an example of something I've already done on one of the pages. Even if you're like on a particular topic, so let's say you go to, I don't know, here we go, tuning hype and parameters. And you're going through and you're like, oh, I liked how he did this. You can always just go, I think even here, yeah, you can go view page source. It'll even show you the RST here, or you can go find the corresponding RST document on the GitHub repo. Just use whatever you see as a template and you're good to go. Any other questions about that? Another thing to note, so I was thinking, so because for the final project, I want to give you a choice to do either a report, like the report for the assignments, or in place of a report, you can give another lecture about what you did. You have like 20 minutes to give a lecture about what you do. You basically lecture your report instead of submitting an actual report. The trouble with that, though, is if everyone wants to do it, that means we're going to need like 5 lectures to cover all those reports. That's like 2 weeks worth of lectures. That means people are going to have like results for their final project like 2 weeks before the end of the semester. So I'm going to have to post the project description details. I guess if people work in groups of 2, it won't be as big. We won't need as many. But in order to give a lecture about what you did, you're obviously going to have like results. So I'm going to have to be careful and thoughtful about how I want to do like the timing on that, but I don't have a solution yet. I'm just letting you know that I'm thinking about it. That's all. Okay. Any other questions? All right, cool. Okay, where on earth did we leave off? I think we were doing, did we finish representation? Integer permutation, yeah, how it's better. Common representations, yeah, permutation, real values, trees. Yeah, I'm guessing we finished that. All right, n queens, there, finally stylized. So, n queens. N queens is, again, it's not a particularly, it's a fine problem. It's definitely a lot more interesting than the bit string maximization, right? That was kind of a silly one. So this is a real problem. So using a GA for this type of problem, again, there's going to be like perhaps better algorithms for solving n queens than a GA, but we can use a GA, and a GA will work well. So let's build a GA to do n queens. The point of this topic is to see, we already built the GA for the bit string, a simple problem. So the point of this topic is to see another implementation of a GA for a different problem. But what I want you to notice is it's basically the same. You just changed out the representation, you changed out the genetic operators, you changed out a few things here and there. And there you go. So I want the emphasis to be on the similarities and the differences in the GA for the 2 different problems. Although, yeah, the first GA implementation was solving a different problem, much of the algorithm is going to be exactly the same. So the problem. The optimization version of n queens is going to be used. Now, when I say optimization version, I want to minimize the number of conflicting attacking queens. When you're doing the like absolute constraint version of n queens, it's either is it a valid board configuration or not. And with that, you don't really have a gradient, right? Your fitness value is basically true or false. Is it valid or not? So the selection for your genetic, like the selection for chromosomes is not going to be, there's going to be like no selection pressure, right? It's either correct or not correct. So instead, we use the optimization version where it's, okay, minimize the number of conflicting queens. Because then you suddenly actually have a gradient. One board configuration with 2 conflicting queens is probably not as good as one with 1 conflicting queen. One conflict versus 2 conflicts. Not a guarantee, but you know, at least there's a bit of a gradient to follow. So yeah, here's an n by n, or sorry, a 10 by 10, 10 queens. This is an optimal solution. Yeah, I already, okay, yeah. Okay. Okay, the phenotype space is the board. Assuming queens are not allowed in the same space, we have n times n to choose n. However, as previously discussed, we saw that we can actually get the number of configurations with a permutation representation down to be n factorial, which is still not good, but it's better than n times n choose n, because, well, that's how math works. So n factorial is still bad. It's a lot better. So we already talked about how we want to constrain our search space with a clever representation. We'll use that permutation representation. I don't think you were here last time, so I'll say it again real quick.
I watched the video.
You watched the video? Okay, then you're in great shape. But yeah, the permutation representation, what's good about that is the representation itself guarantees that no two queens will be in the same row or column. We've already eliminated a lot of invalid solutions, so fantastic. So first, initialization. Before, we need to create an initial population of candidate solutions. All right, permutation representation. What's it going to be? All right, well, we're going to have a chromosome a chromosome. It's just going to be a list of length n, where n is the n in n queens. If I want 8 queens, n's going to be 8 because I need the position of the 8 queens. Each of the n indices corresponds to each of the n queens. Each index will be the queen's respective column. The element within the list will be a permutation of the integers between 0 and n minus 1. I guess it could have been 1 to n, whatever, it's arbitrary. And the value at each index is the respective row. There. Since the values and indices are unique, no two queens can be in the same row or column. An example, there. There is an arbitrary example of what a chromosome could look like with this encoding. So how would we want to initialize this? Randomly generate permutations. We can do that. Python import random, there. You can shuffle to your heart's content. Population, should be easy. Just create a list of the chromosomes. So we have a list of lists, right? Here I realize I represented I wrote the chromosomes kind of as like vectors with the triangle brackets to emphasize the difference. One's a chromosome and the list is the population of the chromosomes. But when I implement this, it's just going to be a list of lists, right? The chromosomes and the population randomly generated. So there we go. There's some code to randomly generate my population. I got a population, starts as an empty list. I have a population fitness list. That's just going to be a list where each index corresponds to the chromosome in the population list's actual fitness based on indices, right? And then for whatever in range of the population size is some arbitrary value I set, right? It's one of those hyperparameters. Then just sample. I'm using random sample. This is an easy way to generate some permutation of those n values. Cool? And then add it to the population, right? Again, I'm seeing like stone faces, and I don't know if it's because it's painfully obvious or you're scared.
So we have to make the population an even number, like.
It's up to you. With me, again, I think I was lazy and I made it an even number. But you could implement it such that it doesn't need to be an even number. In fact, usually what I do when I'm being really lazy, because I like to do elitism, I'll always ensure it's an odd number. But I do the elitism of one chromosome, and then I've got the even number. So usually I usually, when actually implementing it for myself, if I'm solving a problem, I just lazily always ensure it's an odd number. But you could be a better programmer than me and just make it work. For those of you that don't remember, the initial GA I showed you, I ensured that the population size was an even number because I always wanted to select two chromosomes I wanted to do crossover between two adjacent chromosomes. So because I want pairs of two, I just always ensured it was an even number. I was lazy. Yep. There. If you don't believe me, here's a link to the Python docs for random. There you go. Cool. Any questions about that? We're happy. At the end of the day, it's very similar. Look, if I go to the bit string optimization, there's going to be a chunk of code that looks very similar. It's just what I changed out was how I randomly generated the initial population. With the bit strings, I just generated an arbitrary list of zeros and ones. This will give me a list that's assured to be a permutation. So that's really the only difference, is what I put right here to create the chromosome. Otherwise, this code is the same. Evaluation. Well, this one's tricky. The fitness function will count the number of conflicting queens. Each pair of conflicting queens will only be counted once. We could count it twice, but I'm lazy. I'm going to count it once. With the representation used, it's not possible for two queens to be in the same row or column. So all we really need to check is the diagonals. The fitness function is going to be the most tailor-made thing of your GA for the given problem. It's probably obvious, right? Is, well, what's good for your problem? Now, I'm going to warn you, this may not be that clear, but I think it's actually a really simple little fitness function. But it may not be immediately clear. I'm going to try to talk you through it. If at the end of my discussion you don't fully understand how the fitness function is actually working, it's not critically important that you understand it for the sake of the lecture, but it's good if you do. So how does it work? All right. Actually, first let's read the docstring, because it actually describes pretty well what I'm trying to do in the code. So count the number of attacking queens, the provided queen placements. To count each attacking, oh no. Oh no. Oh no. To count each attacking pair only once. The check for attacking only happens in the forward direction from index 0 towards index n. With the permutation representation, attacking can only happen in a diagonal. Thus, the check for attacking is to check only plus minus offsets, where offset is the number of indices away the queens are from each other. For example, consider the chromosome, whatever, whatever, whatever. The question marks mean I don't care what they are, but this is what it is. It's like whatever, whatever, 4, 3, 6, 1, whatever, whatever. The queen at index 2 is attacking 3 queens. It attacks the queen at index 3 as it is offset 1. So the queen at index 4, at index 2, is in row 4. I know it's attacking the queen at index 3 because I am 1 column away and I am 1 row plus or minus its row. I'm seeing people go, what? But it's simpler than you think. Consider a chessboard. I'm here. If I am in the next column, right, the only way for it to be attacking is if I am in a row above or below 1 of where that one is. If I am 1, 2 away, I must be 2 above or 2 below. Right? That's all it's doing. And I only check in this direction, because if I count this way, if I'm conflicting, let's say there's a queen here and I'm conflicting, I don't need to check this way because I've already counted that conflict. If there was a conflict, if a queen was attacking me to the left, I would have already counted that attack. So that's why I can get away with only going in the one direction. So, yeah, and it's attacking the queen at index 4 as it is an offset 2, and 4 plus 2 is 6. Right? So 1, 2, 6. It also, if this was a 2, it also would have been attacking. It was just above, not below. It was the diagonal, it was the other diagonal. Yeah? Right? There we go. All right, so let's look at the code just to talk about it. Start with some running total attackers. For attacker column and attacker row in enumerate chromosome, right? So for those of you that don't remember, enumerate will give you the index and the value in that index for some collection. So attacker column and attacker row. For victim, so okay, only look at victim index is going to be whatever my attacker column is plus 1, because I only need to worry about those that are that way of me. I don't care about any queen in my row or in my column because it's relevant. And I don't care about any columns this way. So I always only look this way to the end. I get the offset. The offset is going to be, really, maybe I should call this victim column. That might be a better name. But victim index minus attacker column will be the offset. How far away, how many columns are they away from me? Get the victim row, well, that is the value at that index to tell me, okay, so they are how many columns away from me? What row are they in now? If the row, if my row minus the offset or the attacker row plus the offset is equal to the victim's row, we've got an attack. Are we happy with that? Yeah? Good. Good. See, it wasn't too bad. It seemed complex. It's not. Maybe I should rename this victim column.
Why didn't you check for the queen above or below the attacker?
Because I'm not looking directly above or below, because it's not, with this permutation representation, it's not possible to have a queen in the same column as me. Because the column is defined by the index, and there's only one index for each index, right? So we only need to be worried about the diagonals, yeah. And we're only looking in the one direction, right? Up this way and down that way. Yeah? Maybe I have a picture here. Yeah, here we go. All right. Can anyone see the 4 conflicts? 1, 2, 3, and then 4.
So can a queen be a victim and be an attacker?
Yeah, but we only count if there's 2 queens, we count that once. So the ones I'm counting are, first and foremost, we can count this. This is 1 attacking, okay? 2, ignore this one, 3, and now 4. This one's kind of a funny one. But again, I'm not counting any pair more than once. I'm counting this pair, I'm counting this pair, and then I'm counting this pair. Yeah?
What about the 3, 2, and 3, 4?
These ones?
Yeah, I'm sorry, maybe I just...
Yeah, you missed that one. We hit that one first because it was the easy one. Okay? So that's the idea. That's the fitness function. And that's probably the hardest part. Well, maybe the crossover is going to be tricky. We'll see. All right, this is just explaining the fitness function. Okay, how do we calculate the fitness? Well, population fitness is an empty list. For each chromosome in the population, calculate its fitness, add it to the population fitness list. Like append it. Good. Selection, let's do tournament selection. I like it. It's easy. This code is basically going to be exactly the same as what we saw in the bit string 1. Mind the use of this direction argument, though. I briefly mentioned this when we talked about the bit string and the tournament selection. By default, it assumes that fitness is to be maximized. But here we actually want to minimize the number of conflicts. So I add a -1, and that's how I can tell selection, no, you want to be more likely to pick ones with lower fitness than higher fitness. By default, it'll do higher fitness. So I added this direction so you can specify what do I actually prefer. Cool? Yeah. And here you can see direction by default, it has a default value of 1. Direction +1 for maximizing fitness, -1 for minimizing. Technically it could be -1 billion, it doesn't matter. It just needs to be a negative number. And all that does is just multiply everything by -1 just to make sure it all works. Or sorry, multiplies it by the direction, which would be -1 if you're minimizing. Cool? So far so good? Variation operators. Now here's a problem. If I did 1-point crossover, we're going to destroy the permutation property. And that's a problem, right? If I have the chromosome 0, 1, 2, 3, 4, and the chromosome 4, 3, 2, 1, 0, and I did crossover in the middle index, 0, 1, 2, 1, 0 ain't a permutation. First, we've got 2 1s in there and 2 0s. And where the hell is 3 and 4? Well, I can tell you where 3 and 4 is. It's in the other chromosome. But the other chromosome doesn't have 0 or 1. So a crossover like this is not going to work very well for us. It's going to be very bad. It's going to immediately destroy the benefit of the permutation representation. So we can't use something like a simple 1-point crossover. Here we're going to do something called ordered crossover. There are 2 very popular permutation-based crossovers. One's called order crossover. The other one's called partially mapped crossover. I'd say order is a little bit simpler to wrap your head around. I will warn you, it's going to feel complex at first, but it ain't that bad. Here's the idea. So first and foremost, this would be an example of 1-point crossover. There's something called 2-point crossover, where with 1-point crossover, you select a point and you exchange everything from that point to the end. With 2-point crossover, you pick 2 points and you exchange everything between the 2 points. It's a little bit more general of a version than 1-point crossover. 1-point crossover is 2-point crossover if the second point is always the end index. All right? This order crossover basically goes, okay, pick 2 indices like you're doing a 2-point crossover. So this image here is going to show an example of how 2 chromosomes generates 1 child. And you would do the exact same thing to generate the other child, but you would do it in reverse. You pick the points you want. So 4, 5, 6, 7, I keep. That goes to the child. Then from the other one, what I'm going to do is I'm going to go, starting after the ending index, I take from the other chromosome all the values in order that are not already in the child chromosome. So I go 1. So the first one I want to add is a 1 after the number 7. Is 1 already in there, though? Because it's possible that 1 came from inside of here. So is 1 already in that chromosome? No. So we can add it. So we add 1 here. The next one I want to add is 4. But 4 is already in there. I skip it. 9. I can add 9. So 9 goes here. 3. 3 is good to add. 3 goes here. 7. 7's already in there. So we skip it. 8. 8's free to go. We put 8 there. 2. 2. We're done. Because the last 2 would be 6 and 5, which are already in there. So that's how we generated this. The other child would be 8, 2, 6, 5. We skip the 8. We add the 9, 1, skip the 2, add the 3, add the 4, skip the 5, skip the 6, add a 7. The other one would look like that. Yeah? Cool? So this crossover, we can actually take a moment to talk about this crossover a little bit. It's permutation safe. It ensures that your permutation remains a permutation. All values are unique, which is very important. But one idea we like to be aware of when talking about our genetic operators is how destructive are they? And there's no absolute way to measure this or make hard assertions about it, but it's an idea you need to be aware of. And it depends on the representation and the problem as well. So, if we were, ignore n queens for a second. Raise your hand if you use this for TSP. Why did you use it? Because it was given to you? Awesome.
It was given to me in permutations for you.
There you go, right? There you go. Now, and what I'm about to say is not to say that this is a bad crossover for TSP. In fact, it's great. But with TSP, think about what the chromosome means. It's an ordered list of cities. Adjacency really matters, right? If this is TSP, if this is an ordered list of cities, the fact that we have 4, 5, 6, 7, that is a very specific route. And maybe evolution has been going on for a while, and that is a good route, right? With this crossover, with TSP, presumably, the fact that 1 comes before 2, which comes before 3, that order is probably a good one if evolution's been going on for a while. That's a good pathway to take. It's a nice 1, 2, 3, 4, 5, 6, 7, 8, 9. For whatever reason, if I visit the cities in that order, I can visit all those cities in a particularly efficient way, presumably. No guarantees, but let's assume it is. So the adjacency is very important, right? With this crossover, I pick some chunk that gets to be preserved. So that portion preserves this chunk. Because, okay, it's good. We preserved a chunk. That contiguous chunk is meaningful. That's good. But then when filling in 1, 4, 9, 3, 7, 1, 4, oh, don't add the 4, we can add the 9. Suddenly, everything else gets all jumbled up. And that adjacency property is kind of thrown away. So, half of this crossover, there's no guarantee it's half, right? Because the 2 points could be anywhere. Some amount of this crossover is going to be really good at preserving some adjacency, some information that's in there, because the information isn't the absolute value of what's in which index, it's the adjacency that's important. So adjacency is going to be preserved for some of the crossover, but the other half of the chromosome is going to be filled in with a very destructive process of just fill in the blanks that work. So there's nothing wrong with this crossover, but it's good at preserving contiguous chunks a little bit, and then really bad at preserving contiguous chunks the other way. Does that make sense? So this would be an example of, well, part of this crossover is quite destructive. When you compare it to partially mapped crossover, I'm pretty sure I would say this one is less destructive than partially mapped crossover. Partially mapped crossover is quite destructive. But if we take this for the n queens thing, I don't really know if I'm so worried about the amount of destructiveness that this causes compared to TSP. Maybe I should be. I don't know if I am. But the point I'm making is there's no absolute terms here on destructiveness. Well, it's a very destructive operator. It always depends on the problem, the representation, and what's going on. Cool? So here's order crossover. This actually has an internal function. I'm going to be honest, this is the first time I ever wrote an internal function in a function in Python, because I've never actually saw a good use for it, and then I finally saw one here, and I was like, sick, I can do it. All right. for those of you that don't know what I mean, in Python, I can write a function inside of a function. I can define a function inside of another function. And it's kind of like, think back to like Java or C++, right? Where you have private functions inside your, private methods inside your classes, which are helpful for internal workings for that class, but really shouldn't be used elsewhere. It's the same idea here, but it's also maybe this function, I can write a sub-function that's really important for this function, but it's not going to be used anywhere else. So I wrote it as an internal function here. So I don't know, it was interesting. I got really excited that I was like, finally I have a good use to use an internal function. So here is order crossover. Source index, target index. Okay, what do we have here? Okay. Parent 1, parent 2, start index, end index, and it returns a tuple of lists, right? Because it's going to return the two children. Source index, target index, mod the length, end index. Not quite even sure what the heck that's doing. Oh, that's for copy missing elements. Let's ignore that part for now because that's the other bit. So, len1. If the parents aren't the same length, this crossover ain't going to work. It throws an exception. If there's an issue with the indices that were specified, raise an exception. Otherwise, make copies of the children, or sorry, make copies of the parents, because remember, we want these functions to be pure. We want to keep our chromosomes immutable. Maybe I should have made them tuples. So create copies. If start index is greater than end index, just leave them alone. If someone specified the indices, the start and end in reverse order, they used it wrong. Just function doesn't do anything. Otherwise, copy missing elements from parent 1, child 1, start index, end index. Start index, end index. Okay. So we call the internal function what's going on. Source index is the end index of parent 1. Target index. Cool. So I have a source index. What this is going to be is source, target. But they can become unaligned, right, if we skip one. So we start saying, okay, I've got this contiguous chunk here. Source, okay, I guess here, in this particular case, we've got 4, 5, 6, 7, right? The source index would be the 1, and the target index would be our, where is 0? 0, 1, 2, 3, 4, 5, 6, 7. So source is 7, target is 7. If I copy the 1 over, we add the 1, we move source to target. 4 is already there, so we move source but leave target alone. So that's what source and target are, to keep track of where we could be copying from and to. All right? Well, target index is not equal to the start index, meaning we're not done. Parent at source index is not in child. If it's not, you copy it over. Increase target index, we might have to loop around to the beginning. Otherwise, move the source index to the next one. That's it. That's all it is. And if you thought, if you didn't follow that, it would take you 2 more seconds to just look at this and make it make sense. You'll be good to go. Long story short, there's a sophisticated, permutation-safe crossover. Any questions about that one? All right. Mutation. Here's an easy peasy mutation that's safe for permutations. Swap mutation. Select 2 indices, swap the values. You're not going to add a value. You're not going to accidentally remove a value. All you're doing is just changing the location of where 2 values were. Swap mutation. Easy peasy, permutation safe. Swap mutation, there it is. This is, I don't know if you know this, you can do this in Python. It's just syntactic sugar. Instead of having to have like a third variable, you know that classic, how do you exchange the values in 2 variables? We need that third temporary variable, right? Well, in Python you don't because you can just do this. And it's actually, I'm trying to remember, but I think it's actually technically faster too. There's like something Python does to make this like technically a little bit faster. Okay, anyways, termination requirement, some predefined number of generations, just like it was with the bit string. So overall, this is what it looks like. For generation in generations, empty fitness, calculate the fitness of everything, do selection, do crossover, do mutation, repeat. That's it. This code is basically exactly the same. It's got the same skeletal structure as the binary string one. The only thing that was different was the crossover, how many random indices I needed to select. The mutation was a little different. Selection was actually identical to before. Fitness was exactly identical except the function that was actually called here. This code is the same. The point of this topic is to see that the GA is the same. It was just the nitty-gritty details that were different. That's all. This is part of the reason people love genetic algorithms. If you know how to write a GA, you know how to write a GA. If I know how to write a GA, I can throw it at n-queens. I can throw it at TSP. I can throw it at you name it. I don't need to know shit about n-queens. I don't need to know shit about TSP as a sophisticated problem. I just throw a GA at it and it'll work. And I get good results. I know I asked this last time, but I'm curious if it's changed now. Raise your hand if you more or less have a working version of assignment 1. Really high, I want to see. Yeah. How long would you say it took you to get a working GA for TSP? It doesn't necessarily need to be giving you good results. How long did it take you to get it working? 2 to 3 hours? How about you? 2 to 3 hours, 2 to 3 hours, yeah. 2, yeah, that's it. That's it. And I'm willing to bet next time you have to make a GA, it's probably going to take you 1 hour. Because 2 of those 3 hours were probably you going like, wait, I gotta know what a GA is, right? The first time you implement it, it's going to be a little harder. After that, that's it. It's easy, right? I'm often really careful about using the word easy because easy might make it sound like it's trivial, which you never really want to do. And also, easy is in the eye of the beholder, right? No, a GA is easy. And if you don't think it's easy, you're doing it wrong. All right? And I got news for you. Genetic programming, the next assignment is going to be about genetic programming. It's also easy. PSO, particle swarm optimization, it's also easy. This is the secret of this course, is we've got all these big crazy ideas. They're just high-level ideas. You just got to make it work. You've got a really easy-to-make algorithm that'll give you damn good results. That's the secret of evolutionary algorithms. That's it. Any last questions? We're out of time. All right, cool. I'm going to go update. When I get back to my office, I'm going to update what I have on that lecture page to give slightly more details, like email me by such and such a date. Yeah, anyways.